This is the Gold Coast of Australia. Population 560,000. It's late Sunday afternoon. This is Brisbane, 70 kilometres away. Population 2.3 million. It's early Monday morning. And here's the traffic between the two cities on the M1. 150,000 cars a day, 365 days a year, travelling 70 kilometres. This journey is duplicated on freeways worldwide, and collectively drivers use about 1,000 barrels of oil every second. Now here's a question. By definition, acceleration is change in velocity over time taken. All these drivers have their foot on the accelerator, but they're not changing velocity, are they? The speed limit is 100 kilometres an hour, and they appear to be sticking to it. That is, they're travelling at constant velocity, not accelerating. So what's going on? The answer to this question is that on a straight flat road, after you've reached 100 kilometres an hour, all of that extra fuel provided by the accelerator goes into overcoming kinetic friction. This is not the common order of the universe. This spacecraft will circle the Earth for eons unless acted upon by a force. Notice there's no rocket propulsion. It's just been silently rotating 40,000 kilometres every 2 hours since it was launched. No friction, no fuel. Unlike the spacecraft, if we slide this wooden block across the desk, it stops. Friction comes about through imperfections in the surface of materials. This wooden block appears to be smooth, but under the microscope we see that it's not. Imperfections interlock as one surface moves over the other. This is like the interlock of fingers. The greater the weight, the greater the interlock, the greater the effort required to push. This is friction. Polishing this steel cylinder reduces friction, but tiny imperfections remain. The piston moves 2,000 times a minute, creating friction against the walls of a cylinder. Many other moving bits exacerbate this problem. To measure friction, we require a variable force. This is provided by gravity elegantly. These are gravity vectors, and this is a block and plank. At this extreme, the gravity vectors are parallel to the red weight vector. Friction on the block is maximum since gravity is acting straight down. Using the finger analogy shows that interlock is also maximum and the block is hardest to move. As we raise the plank, the green vector indicates the reduction in gravity pushing the block towards the plank. The number of pink dots represent the increase in gravity pushing the block towards its inevitable slide. We'll now search for a pattern. The result will be recorded in each of the blue boxes as a gravity vector is traversed. This time we'll assume the friction is enough so the block won't drop until theta is 90 degrees. The green vector is reducing as theta is increasing. The number of pink dots between the vectors is increasing as theta is increasing. We see that friction is a cosine function since it decreases as theta increases, and acceleration down the plank is a sine function since it increases as theta increases. We can make an equation for the acceleration down the plank. A is equal to g sine theta minus the friction, which is the coefficient of friction for wood on wood, U, times g cos theta. Tidying that up, we can say A on G is equal to sine theta minus U cos theta. When A is equal to 0, just like the cars on the freeway, we can say that 0 is equal to sine theta minus U cos theta. Transposing that, we can say that U cos theta is equal to sine theta, or U is equal to sine theta on cos theta is equal to tan theta. U is equal to tan theta whether we're looking at kinetic friction or static friction. To measure kinetic friction, we need an accelerometer on the sliding block. An iPhone is perfect since it has an accelerometer on board. The dynamic range of the plank and iPhone apparatus is from 0 to 9.8 metres per second. In the orientation shown, it's negative 9.8 and 0 when it's falling straight down the plank. When the iPhone slides, the acceleration is measured between the two extremes on the cliff. In this example, the slide is 45 degrees, so the cliff is between negative 2 metres per second and negative 6 metres per second, or a difference of 4 metres per second. The strategy is to slide the phone down the plank at 3 different angles, graph the results and extrapolate to 0. So let's do it. We can analyse each graph in turn. So for 60 degrees we get 8 minus 2, which is 0.6 G. For 45 degrees we get 0.4. For 30 degrees we get 0.23 of a G. Now we can plot each of these in turn. So for 60 degrees we get 0.6, for 45 degrees we get 0.4, and for 30 degrees we get 0.23. We can join those up and we get an intercept here of 10, maybe 12. So tan of 12 is equal to 0.123, or the coefficient of kinetic friction is equal to 0.123. This graph, published in IOP in 2016, shows a more thorough approach, where each of the 10 blue data points is an aggregate of 5 trials. The strategy is the same as the experiment we just performed. We need to know the friction when the acceleration is constant, So each of the 10 data points is extrapolated to 0G. This technique is not necessarily limited to the friction between an iPhone and a plank. You can stick almost anything to an iPhone, and the plank can be any suitable material, for example glass, wood or plastic. Why use an iPhone? Because there's an accurate accelerometer and data logger on board for free.